Hello everyone, welcome back to Math with Allison. Today we're continuing our series, so we're putting the previous two videos together and we're going to work on the first derivative test. So the first derivative test is used to find intervals of increasing and decreasing and mainly to find the local and absolute extrema, if any. So let's go ahead and dive into it. We have an example here and we are going to do both those things. So let us go ahead and solve this thing. First, when we find the intervals of increasing and decreasing, we need to find the first derivative. So let's go ahead and find f prime of x. And this is going to be equal to 12x to the power of 3 minus 12x to the power of 2 minus 12x and then plus 12. So what we can do next is go ahead and factor it a little bit, right? So if I take a 12 out of everything, I'm left with x cubed minus x squared minus x plus 1. So what we do next is we can use factor by grouping. So if I group these first two together and I can group these second two together, we can make them very similar. So what I mean by that is that 12 is still hanging out here. But first, let's go ahead and pull a term out of those blue ones. So I can pull out an x squared, and I'm left with an x minus 1. So notice it's pretty similar to the pink part, but we need to make them the same. So if I do that, I pull out a negative 1, and now I get x minus 1. So now we have that they have a term in common, right? They have this x minus 1. That means we can go ahead and pull out that x minus 1. So we get 12 times x minus 1, and now we multiply it by the leftovers. So what I mean by the leftovers are going to be this x squared and this negative 1. And so that becomes x squared minus 1. Looks like we can factor this one more time because right here we have a difference of squares. So I get 12 times x minus 1, and now that becomes x minus 1, x plus 1. So I'm going to go ahead and highlight this because this is our most simplified form of the derivative. So our next step is to set this equal to 0 and solve for the critical values. So setting this equal to 0, I get 3 terms. X is equal to positive 1, and we get that multiplicity 2, and x is equal to negative 1. So let's go ahead and set up our number line. So first we set up the critical point. So I have a critical point of negative 1 and positive 1. And remember, we test points into the first derivative because if they're positive or negative, that tells us if our function is increasing or decreasing. So let's go ahead and find some test values. A nice easy one, we get a 0, and let's go with 2 and negative 2. And remember, we're plugging this into our derivative. So let's go ahead and set that up. So sometimes I don't care to do all the math. I don't want to multiply 12 times 3 times 3. So what I'm going to focus on is if this is positive or if it's negative. So if I notice here, I have 3 negatives, which is going to result in a negative value. So that means it's negative, my derivative is, and that means my function is decreasing. I'm going to do the same thing with our other two values. Again, here I have 2 negatives, which is going to result in a positive value. Here I have no negative value, so I for sure have a positive value. And now here we have our intervals of increasing and decreasing. So remember, the second part of this is we want to identify the local extrema. So the local extrema occur when the function changes from increasing to decreasing or decreasing to increasing. So notice here at x equals 1, we're not going to have a local minimum or a local maximum because it's increasing on either side of it. So the only point that we're going to be worried about is this x equals negative 1. So let's go ahead and plug this into our function. F of negative 1 equals so I got a corresponding y value of negative 10. So how I would write this out is because we did that little sign chart, I can tell I'm going to have a local minimum. That's why it's really great to have visuals. So if I write that out, we have f of x has a local minimum. Okay, so we have a local minimum at negative 1, negative 10 because f prime x changes from negative to positive. So let's go ahead and take a look at our actual function. I have it graphed out right here. So we can see here our function is decreasing. So it's decreasing, decreasing, decreasing. And then we actually hit our local minimum. And that's going to be at -1, -10. In our case, it's actually going to be our absolute minimum because our function is increasing on either side. So then after that, we change from increasing. We hit our other critical value where it flattens out, but it continues increasing again. And so it's neither a local minimum or local maximum. So that's how we can use the first derivative test. I have it written out all officially here, so let's go through this. Suppose f of x is continuous and has a critical value at x equals c on some interval. Assume that f of x is differentiable on that interval, except possibly at x equals c itself. So first we have if f prime x changes from positive to negative as x increases through c, then f has a local maximum at c comma f of c, so that corresponding y value. Let's go ahead and see why. So I have our number line right here, right? And what we want to do is note that f prime x changes from positive to negative. And if I draw that out, I have our function is increasing and then it's decreasing, which is why we end up with a local maximum, because this kind of looks like a maximum. So very similarly, if f prime x changes from negative to positive as x increases through c, then f has a local minimum at c comma f of c. So if we change from negative to positive, that means our function goes from decreasing to increasing, and now it looks like we have a little minimum, right? And so we can see that dip in the function. So now this is the special case that we had. If f prime x is positive on both sides of c, so something like this, we have positive values, which means on either side of c that it's increasing, or it could be negative on both sides of c, so we have negative, negative, our function is decreasing on either side. Then there is no local extrema there, so we don't need to worry about it. So using the official definition of the first derivative test, we're going to go through a couple problems. So apply the first derivative test to f of x equals x times the square root of 4 minus x squared on the interval -2 to 2, and we want to identify any absolute or local extrema. So let's go ahead and dive into it. First, we need to find the intervals of increasing or decreasing. So let's go ahead and find our first derivative, f prime of x. So in order to do that, we're going to have to use product rule. So I'm going to go ahead and set it up. We can see our two different products here. Alrighty, so let's find these derivatives. So the f prime is just going to be equal to 1. But in order to find g prime, I'm going to have to apply chain rule. So let's set that up as well. We have our inside u is going to be 4 minus x squared. And then our outside g of u is going to be u to the 1/2. So in order to find u prime, we get -2x, and then g prime of u, we're going to use power rule, and we get 1/2 u to the -1/2. Now we can use this in order to find g prime, so we get -2x times 1/2, and let's plug u back in, so 4 minus x squared to the -1/2. And if we wanted to simplify that, we could a little bit, right? That 2 is going to cancel out with the 1/2. So now we can find the actual derivative. So remember, we just got to multiply these together and add them up. So first we get 4 minus x squared to the 1/2. That one was multiplied by 1, but don't need to write that. And now we're going to add x times -x, 4 minus x squared to the -1/2. So let's go ahead and simplify that out a little bit. I made sure to highlight it because it's our most simplified form of the derivative. And now what we want to do is set that equal to 0 and solve for x. So first I'm going to move that second term over. And now what I want to do, because I have that 4 minus x squared to the 1/2 in the denominator, I'm just going to multiply it over. So I'm going to multiply both sides by it. So now when I add those two exponents, that's really nice. 1/2 is equal to 1. And so here I get 4 minus x squared is equal to x squared. So adding x squared to both sides. Okay, and now we have our critical values. So we have x is equal to plus or minus the square root of 2. Be careful before we make our number line, we always have to pay attention to illegal values. So in this case, we cannot divide by 0, right? Which means that the denominator in our derivative, so one of our denominators is this right here, cannot be equal to 0. So notice here, when does this function equal 0? That's going to be when x is equal to plus or minus 2. So we have to pay attention to that when we create our interval. Because originally, our interval was working from -2 to 2, but it included those two values. So that means I'm not going to include that -2 and that +2, so I left it as open parentheses. Okay, let's go ahead and fill in some values. So the very nice one, I'm going to choose 0. But what do I choose on either side of these? A good known fact is maybe that 1.5 is greater than the square root of 2. So that might be a bit of memorization, but that's a good little fact to have in our brains because now I can apply 1.5. So I'm going to go ahead and fill these in. I'm going to plug them into my first derivative and find out if my values are positive or negative. That took a fat minute. So here I ended up with a negative value. So I have that negative, 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 which tells me my function is decreasing. So the very nice part of having to do this is you only have to do the 3/2 once. If I were to plug in positive 3/2, well, notice here that both of them are squared. So you end up with the same value, right? A negative squared makes a positive. So that's also going to tell me that this interval right here is going to be negative and my function will be decreasing. So that means all we're left to plug in is 0. Okay, I got a positive value, which tells me that my function is going to be increasing. So, looking at our intervals of increasing or decreasing, we want to take a look at where our local extrema is going to be. So it looks like I'm going to have a local minimum at -√2, and I'm going to have a local maximum at the square root of 2. So let me go ahead and write those out. Okay, so now what we want to do is see if any of these local extrema are actually going to be the absolute extrema. So remember, in order to do that, you just got to plug in the values and see which one's the biggest and which one's the smallest. In our case, we did not need to worry about the endpoints -2 and +2 because those were our illegal values. We can't plug those in. So let's go ahead and find them. Okay, so between our two values, first I got a value of -2, and second I got a value of +2. And so this means they're going to be my absolute extrema, right? So I can write that out. Okay, let's go ahead and compare that to our actual function right here. So we can see that we hit a absolute maximum right here at negative square root of 2, -2. And we hit a absolute maximum right here at the square root of 2, comma 2. And so looking at our intervals of increasing and decreasing, we first start by decreasing until we hit our absolute maximum. And then we switch over to increasing, right? And we're increasing between our two critical values, which we did get on the chart. And then finally, after that, we are once again decreasing until we hit the value of 2. And so I want us to also notice right here, I'm going to erase this, that at -2 and +2, we're going to have a vertical tangent line, which is why our function is not differentiable at those two values. So what I mean a vertical tangent line, it just means that it goes straight up and down, which means the slope of it does not exist. So let's go ahead and try another example. We're going to apply the first derivative test to a polynomial, so -x² minus x plus 2 on the interval -4 to 4. So let's first find our derivative. When we do that, we get negative 2x minus 1. And it looks like that's pretty simplified, so we can leave it like that if we want. And we can go ahead and set that equal to 0 and solve. So I get negative 2x is equal to 1 if I add that over. Dividing both sides by negative 2, I get negative 1/2. So we only have one critical value. Let's go ahead and set up our number line. We don't need to worry about any illegal values, so now we can actually include the endpoints. We can include negative 4, positive 4, plug in our critical value at negative 1/2. Alrighty, let's go ahead and test some points. So first in this interval, let's just go ahead and plug in negative 1. And over here, we can plug in 0. I always suggest plugging in 0 if you can. It's a nice one. So f prime at negative 1 is equal to... Okay, so just looking at this, I know for sure I have a local maximum at negative 1/2. But we need to test for absolute extrema right now. So remember, when we do that, first we're going to plug it into the original function. We're not going to plug it into the first derivative like we do for testing for intervals of increasing or decreasing. But we are also going to plug in the endpoints, right? We have to see if that's going to give us any absolute extrema. So let me go ahead and do that. Okay, let's go ahead and look at our values. So we got negative 10, 2 1/4, and negative 18. So looking at this, I can see for sure I have an absolute minimum and I have an absolute maximum. So let's go ahead and write those out. Let's go ahead and see what that looks like on the actual graph. So I have that graphed out right here. We can see very nicely that we do have an absolute maximum occurring, and we also have an absolute minimum, right? And that's going to be on the endpoint. So just like we talked about, our function goes from increasing, we hit our critical value, and we go back down to decreasing. Well, that's all I had for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They are linked down below. Otherwise, please leave a thumbs up and comment other topics or problems you'd like to see done. Thanks for watching.